This project is part of the Flexeo project, which is the fabrication of a prototyping card suited for flexible electronics. So prototyping card started with Arduino, which made it possible to do some demonstrator and to quicken the way that we do prototyping in electronics. So there has been some attempts to do some flexible cards, which has the Arduino system on them, but they still require rigid connectors. So today I would like to introduce you to the flexible capacitive connectors we've made for our Flexeo. So a few words about this Flexeo project. So it's composed of a core layer that you can see here with a microcontroller. So a lot of applications need a microcontroller, and this is what we have on the core layer, plus a battery which is not plugged on this example. And here we have the application layer. So the application layer will have a sensor, an actuator, or anything needed which is application specific. And what we want is a connection that is modular, which means it's possible to remove the application layer from the core layer and to stick another application layer at will. This means that we cannot solder the application layer to the core layer, because each time we will want to plug a new application layer, we will have to remake the whole core layer, which is, well, not the point of this Flexeo system. So we wanted no rigid connectors, so we had the idea of developing a capacitive transmission. So we have a mechanical contact, but no ohmic contact between the core layer and the application layer. So how to transmit standard data bus, which is a Serial Peripheral Interface, maybe some of you are familiar with it, through a capacitive connection, even though it's supposed to be transmitted with an ohmic connection. So first we are doing some modeling of the interaction, and then I will prove with some experiments that this bus works quite well. So electrical modeling, so here is our core layer, which will be our emitter for this presentation. We have, so it's equivalent to our signal generator. And here we have our very important capacitive interaction. So we have on here the core layer on the bottom with some electrodes, and on the top we have the application layer with some electrodes. We have a dielectric in between, which is in this case Fayolle, which is our substrate, plus PVA glue to do the mechanical contact. And it is equivalent to a capacitor. Here we have our application layer, and the reading will be equivalent to this system. Note that the system has a complete floating ground, so there is also a capacitive coupling for the ground, which is visible here, and the equivalent capacitance of these two is visible here. So we've done the both diagram of the system, and two things that are very important is that it is a high-pass filter, so we will be only able to transmit high-frequency information through the filter. And another thing is that the equivalent capacitor I showed earlier is present in both the gain and the cutoff frequency of the system. So this is really the point of focus of this presentation, is what is the condition of these two capacitors to ensure a good transmission. So to do so, we will see what happens when we try to transmit, for instance, the clock of the SPI transmission. So here we have a signal generator, and this is simulation based. So the goal is to attain the high threshold. So this will be, if a voltage goes higher than this line, this will mean that the receiver will be able to detect the ones of the transmission of the clock, which is our goal here. We can see that when we plug a high pass filter, we have, well, a filtering of the system, which means that the value of the voltage is going to be around the mean value of 0 volts, which means that we will never be able to reach this threshold. However, I showed earlier that on the equivalent model of the receptor, we have some diodes here, and fortunately, this diode will clamp the voltage received, and this will rectify the voltage for us. And so we have two main losses in our system. The first one due to the gain of the high pass filter, and the other one due to the diode. So when we plug in the values in the datasheet, we can calculate a minimal coupling capacitance here of 23 picofarad. Something very interesting we have in our case, and which differs from a classical electromagnetic transmission, etc., is that we have several pins that are discussing at the same time in our system. We can see here, for instance, we have two pins, so one is the clock, one is the data, for instance, and both are putting current through a single pin. But all the current is going back to the same ground coupling. So we will have a variation of the potential of the floating ground, which impacts the different pins. So current on pin 1 will impact pin 2. However, we can see with other simulations that as the capacitive coupling of the ground increases, we have a diminution of the variation of the potential of the floating ground. So if we want to avoid more than 1% of variation of the floating ground, we can simply ensure that the ground coupling is 10 times higher than the capacitive coupling. In practice, this is easy to do with a big ground coupling next to the pin. And with some calculation, we go to 230 picofarads for the ground coupling. So does it work in practice? Well, we evaluate the packet error rate of our system. So we will count the number of missed SPI communication divided by the total number of SPI communications. So if anything goes wrong, the value is not good, so nothing is transmitted, it counts as an error. It's very binary. And we have here a microcontroller and a temperature sensor, which is communicating with SPI. And we tested with, for now, a physical capacitive coupling in between. So here are the results. And you can see that as we increase the value of the capacitive coupling, we can see that the error rate is decreasing quite fast. And at 18 picofarad, we can ensure a stable transmission and a stable SPI transmission between the microcontroller and the temperature sensor. So our experimental value for the coupling is 18 picofarad, which is quite close to what we've simulated before. Is it still true on ultra flexible substrate? Well, we've tested with two mechanical couplings. So the first one is PVA glue. Maybe you know this material. The other one is PDMS glycerol. So this one is the best one because PDMS is naturally sticky. So that means that we will have our effect of sticking the application layer, and it will be easy to remove it and to put another one at the same place. And we can see that as we increase the size of the electrodes, we increase the capacitance of coupling, and so the error rate is also dropping dramatically. And we can see that after, when we reach 3 millimeters of the diameter of the electrode, we have a 0 error rate, so we have a stable connection between our microcontroller and temperature sensor with the SPI going through this capacitance here. So capacitive contact is compatible with ultrathin electronics with an electrode size of 3 millimeters of diameter. So a short conclusion, we've made a modeling of a capacitive coupling transmission between microcontroller and temperature sensor. And then we tested physically, and we were able to obtain a 0% error rate for parts that are at least 3 millimeters on our Parylene substrate with a PDMS glycerol interface. And we've made the first demonstration of a capacitive standard bus on flexible electronics. So the further study, the most interesting study that we want to do is here. You can see that we still have some wires connected to the system, and we want to avoid wires as much as possible. So we want to do capacitive coupling to also power the system. So with the RLC resonator tank using this last part that is still under development. Thank you very much for your attention, and I will be pleased to answer a few questions if you have.